All right, this is Unit 1, and we are reviewing everything. So this is a good review right before a test that you might have on all the concepts in Unit 1. And the Unit 1 AP stat here is exploring and understanding data. So here we go. How fast do horses run? Kentucky Derby. And by the way, before I continue, remember, if I'm moving too fast, pause the videos, write the problems down, or at least a summary of the problems, and then try them out before I basically give you the answer. So the Kentucky Derby winner's top 30 miles per hour, as shown in this graph. The graph shows the percentage of Derby winners that have run slower than each given speed. Note that few have won running less than 33 miles per hour. But about 86% of the winning horses have run less than 37 miles per hour, right? So few have run, right? And then their speed, this is percentage below. Most people who started to win were racing above 36-ish miles per hour, right? Once you get up here closer to, if that was 35, 36, 37, it's looking like it's getting steeper as it goes, right? This is the cumulative frequency graph, all right? And they call those also the ogive. Estimate the median winning spread, which means the middle. Estimate the quartiles, okay? Estimate the range in the quartiles. Create a box plot with this estimate, all right? So here's what we got. The problem sounds wordy, sounds more difficult than it is. The median speed is the speed at which 50% of the winning horses ran slower. So I have to find about 50%, and these are the percents. So pulled over here, and as I do that, that's why it says and down to speed, it's about 36. It's about where that is, right? So point is, if that's where about 50% or the median is, then we know that the median is about 36%. That's about the middle. In part B, I want to find quartile 1, and I want to find quartile 3, or I'm not going to be able to find anything. I believe it just estimate the quartiles. So I'm not going to be able to find the interquartile range otherwise. So about 25%. Well, if that's 30 halfway, right? When we go about half, it says quartile 1 is 25%. And quartile 3 is 75%. So matching these to give you quartile 1, if you look, I would say that's half again. It's about 25. Go over. On there, we're going with about 34.5. 75% would be that 70 up a little bit over, and that's looking about 36.5. So I can bite those, what they're given, right? If you were to do a rough estimate. It wants the range, right? So if I want the range of the whole thing, the lowest value looks like it's probably around 31. The highest value looks like it's about 30, maybe even higher, around 38. But what they're wanting is, if you scroll the whole way back, so it's estimate the range and the interquartile range. That's why we're doing both. So they're estimating that the interquartile range is about 2 miles per hour, but the low seems to be somewhere around 31. The max, if that is in between there, that's about 37. That's about 38-ish out here. So I can bite on the 38. So the range is that. And then it says, and approximate to approximate to approximate a box plot, we need the low and the high, which we have. We need the quartile ranges and the median. So basically, to approximate that dot plot, or the box plot, I have my low and my high that we found. I have my median, right? And I have my quartile 1 and 3. And it's looking like the data might obviously be skewed to the lower end. Well, the lower end would actually be skewed to the left, which is where that's coming from. That's why, even though it's skewed down this way, you're like, isn't that to the right? Well, actually, the lower numbers, if you look at it that way, are skewed to the left. The lowest winning speed is just under 31, and the fastest is just above 37.5. The median speed is approximately 36, and 75% of the winning speeds are above 34.5. Only a few percent of winners have had a speed below 33. Only a few. And think about it, that's, who knows when that was, right? Or what happened to the horses during that time frame. So let's take a look at this one. It says the Framingham Heart Study recorded the cholesterol levels of more than 1,400 men. And here is the AGIV, or which we now know as the cumulative frequency distribution, right, of these cholesterol measures. And basically, that's why we went over this backwards and forwards, so you could figure out how a regular frequency would look. If it looks like it is steadily going up, right, it's not like up to start, we want to construct what we think the box plot is roughly going to look like. And I'm going to show you how that looks, because this is the cumulative frequency thing. But again, even though it's a cumulative frequency, we can construct a box plot, because we can again do what we were doing before. And if you notice here, around 50% would be right in here to 25-ish. There it is, right? Quartile 1 would be about 25%, so it would be right around in here, which is pretty close to 200, right? As we're trying to do this. Quartile 3 would be 75%, which would be pretty close to around here, which is right underneath 300, which is what they have. The high is definitely above. This is about 75. This is about 75. So it's it's definitely above 400, right? And the low is down there. If we're going by 75s, probably possibly even lower than that, to be honest. But the point is, we constructed a rough graph. All right, and it says right a few sentences, and it says a box plot of this distribution of cholesterol levels 14 is right here, and the 5-number summary is estimated from this to be roughly, there's the high and the low of the high, the quartiles, and that one, and it's just a rough estimate. You can only do so much with this. You draw the lines and you roughly guess what you think it all is. The distribution of cholesterol levels is skewed to the right and tightly clustered around the median, right? It looks pretty close to the median. And if you were to look, it's definitely skewed a little bit that way to the right or the higher end. All right. The median cholesterol is around 230, which we found, which is the middle. And the cholesterols, so the middle 50% of them on the quartile range are from roughly here to here, which is about 60. And a very small percentage of men have cholesterol below 150. Not many of them at all. Right. Even right here is only 25% of them. And right here is only 25% of them as well, and that isn't even that long. Take a look at this. It says, suppose your statistics professor reports test grades as z-scores, and you got a score of 2.2 on an exam. As a z-score, write a sentence explaining what that means. Well, again, that means that you probably did pretty good. You actually did a little above what a usual score is, right? Because that's above the mean, so whatever it was, you did pretty well. But not only did you do pretty well, you're more in the unusual side of it. So it means that you scored above the mean. Taking a look at this one of the authors has adopted a grandson whose birth family members are very short. After examining him at his 2-year checkup, the boy's pediatrician said that the z-score for his height relative to American 2-year-olds was negative 1.88. So he's below that. He's barely within what's usual, because remember, negative 2 and positive 2 are common standard deviations, so it is still normal what he has, but it's technically on the lower side of normal. So he's a little below, not a little, so he's pretty close to being a little unusually short. The mean score of the stats exam was 75 points with a standard deviation of 5. And Gregor's z-score was negative 2. How many points did he score? Well, basically what we can do is, if I know the z-score, and I know the average or the mean, and I know the standard deviation, I can find what that score is by multiplying and then adding. So we basically were able to figure out that it was 65. And again, this is why you need to know the z-score formula, because sometimes you do have to do a little bit of math to manipulate how everything looks. Taking a look at this one, it says, you got some agricultural scientists and are working on developing an improved variety of Roma tomatoes. Marketing research indicates that customers are likely to bypass Romas that weigh less than 70 grams. The current variety of Roma plants produced fruit that averaged 74 grams, but 11% of the tomatoes are too small. It is reasonable to assume that a normal model applies. So boom, right there. Now that I know that a normal model applies, it says what is the standard deviation of the weights of these. Now, this is key to be helpful because I don't currently know the standard deviation with the data. All right. So as we're looking through this to find A, I know the 70 because it says they are likely to bypass them if they are less than 70. So that's a number I know. And I know that that is 74. So my point is I need to figure out what 70 is. As in, like, let's find the z-score. Because it says here, marketing research indicates that customers are likely to bypass raw produce fruit that average 74 grams, but 11% of the tomatoes, of those tomatoes are too small. So what do? Is we do our inverse norm. And with second vars, we do inverse norm to 11%. And if that is 11%, to figure out exactly what that value happens to be as a z-score, we just plug in 0 for the mean and 1, and we end up getting negative 1.22 is the z-score. Okay. We don't know the standard deviation. So my point is, because I don't know what that is, it says we're trying to find that. So what is the normal, what is the standard deviation of the weight of Romas now being grown? That's the only information given. So the only way we can find this, now that I know that, is multiply by that, I subtract them, divide, and I get 3.260 as the standard deviation, which is again reasons why we have to know this. So according to the normal model, the standard deviation of weights of Roma tomatoes now being grown is about 3.26 grams. Now it says, scientists hope to reduce the frequency of undersized tomatoes no more than 4%. One way to accomplish this is to raise the average size of the fruit. If the standard deviation remains the same, all right, what target mean should we have? So same, that's 70 right there. All right, but now they're saying they want no more than 4%. So no more than 4%, so we go and do this again. The second vars, inverse norm of 4%, but 0.1 for the mean standard deviation. And that's how we get this negative 1.751. I know the standard deviation, and I know I'm looking for 70, but they're saying what should I make the new mean? So I multiply by that, I subtract 70, and then divide by a negative to get 75.71 as the mean that we are shooting for. So that is the target grams that we should be looking at to make that the case. The researchers produced a new variety with a mean weight of 75, which meets the 4% goal, right? What is the standard deviation of the weights of these new ones? Well, now we know that it is 75. We still know that we're talking about 70 is what we're looking for here. The 4% lower we just did, that was negative 1.75, so we multiply it, that's negative 5, right? And then after that we divide by that to get our new standard deviation. And then, based on the standard deviations, compare the tomatoes. While the weights of the new tomatoes have a lower standard deviation than the weights of the currents, the new tomatoes have more consistent weights. So if the standard deviation is smaller and more concise, then the new tomatoes are definitely more concise and around that weight. All right, when we come back, we'll start with some bananas.